Let's go over energy. So we have two major types of energy. Kinetic energy, which is the energy of motion. And we have potential energy, which is stored energy. The conservation of energy law states energy cannot be created or destroyed. It is conserved, meaning stays constant. For a closed system. Basically, if we have a closed system, some region of space, if no energy is going into the system and no energy is leaving the system, then the energy inside this bounded region of space is constant. So cases in which we might see losses or changes of energy, so if you had a box sliding on a floor that has friction, and if our system was only the box, we would notice energy decreasing. That's because some of the energy from the box would be going into the floor due to friction. So some of the energy is leaving the system, and so the energy inside the system is not constant. But if we have no energy leaving, and no energy going into the system, then energy inside is constant. We also have the concept of mechanical energy. Mechanical energy, let me see if I can get a proper definition. Um, so in mechanical energy is energy that is possessed by an object due to its motion or due to its position. So mechanical energy is due to motion or due to position. The principle of conservation of mechanical energy states that in an isolated system, in a closed system, one where energy isn't flowing in or out of, is subject to only conservative forces, then mechanical energy is constant. It's also the sum of potential energy and kinetic energy. I like thinking of it as mechanical energy ignores like the chemical bonds because there's energy in the chemical bonds. It's just mostly due to position and motion. energy due to position and motion, and it's equal, so mechanical energy is equal to potential energy plus kinetic energy. And ignoring friction, so we have no friction, then mechanical energy stays constant. Is a very simplified expression. So if we have no friction, then mechanical energy stays constant. So let's look at some common equations for kinetic energy, potential energy. So kinetic energy is equal to 1/2 times mass times velocity squared. KE equals 1/2 mv squared. From this equation, we can get the units for kinetic energy. Kinetic energy is equal to, this has no units, mass, the units of mass, times the units of velocity squared. So the units of mass is a kilogram. The unit of velocity is meters per second, but this is squared, so meters squared per second squared. And that's equal to kinetic energy, the units of energy. We usually call energy units joules. So 1 joule is equal to 1 kilogram times meter squared per second squared. So this is going to be our main equation. We also have potential energy. And potential energy can come about by various different forms or causes. We have gravitational potential energy, which is equal to mass times acceleration due to gravity times position or height above some reference point. And that reference point is height above ground. We usually let ground be 0, and that's our reference point. Note the universe only cares about changes in energy, not exact values. So what this means is if you had an energy of 10 joules and you decrease it to 5 joules, you've extracted a total of 5 joules of energy. That's the difference of what you started with and what you end up with. That difference of energy is how much you extracted. It didn't matter if it originally had 1,000,010 joules of energy, and you decrease it down to 1,000,005 joules. The total energy didn't really matter. Hence the reason why we're able to set the ground at 0 instead of the center of the Earth. So gravitational potential energy equal to mgh. We also have elastic potential energy. And that's equal to 1/2 times some constant, usually called the spring constant, times how much is compressed or stretched. So position squared. So elastic potential energy is equal to 1/2 times some K times X squared. The unit K is measured in newtons per meter. Hold on. I think I'm leaving something off. Those units don't. Oh, it's newtons. It should work out. Yeah, that's right. It's also known as spring potential energy. So some examples. Suppose we have a ball that is 5 kilograms and it's moving with a speed of 10 meters per second. So the mass is equal to 5 kilograms. Its velocity is equal to 10 meters per second. We can figure out the total kinetic energy it has. Kinetic energy is equal to 1/2 times mass times velocity squared. That's 1/2 times 5 kilograms times 10 meters per second squared. That's 2.5 kilograms times 100 meters squared per second squared. And that's equal to 250 joules. We can have a table, or a ledge, as it say. So let's say we have some sort of ledge, and let's let our reference frame right here be the ground. So this is where we'll go call 0 meters height. And let's let this height right here be equal to 2 meters. And let's rest on top of it a 5 kilogram ball. We can figure out the potential energy due to gravity. Equal to mass times g times h. The mass is 5 kilograms. Acceleration due to gravity on Earth is 9.8 meters per second squared. And the height above our reference point, the ground, is 2 meters. So 5 times 2 is 10. 10 times 9.8 is 98 joules. Suppose we had a spring. So think of like a pinball ball. You have some spring. At the end of it, we have some mass. And suppose we compress the spring back So let's let the original distance, so from here to here, let's let that be 1 meter. And we compress it down to this height of, let's let it be 6 meters, or 0.6 meters. This x, so our spring constant, is potential energy due to elasticity. So elastic potential energy is equal to 1/2 times k times x squared. This x is how much we compressed it by. So from here to here, we compressed the spring by 0.4 meters. And let's let the spring have a stiffness. So the spring's stiffness constant, or spring constant, let's let it be 100 newtons per meter. So that means it takes 100 newtons of force to compress the spring for every meter is compressed. So how much energy is stored in it? If we were to let the ball go or let the spring go, we're putting energy into the spring. As soon as we let go, the spring's going to snap back and release that energy into the ball. So our spring constant is 100 newtons per meter. We compressed it by 0.4 meters, and we square that term. So that'd be equal to 50 Newton meters times 0.16 meters squared, which gives us 8 joules. These are going to be our main equations, and here's different types. Let's now look at the conservation of energy. So let's go back to that ramp problem we did a while back. So let's say we have a steep ramp. And we have a box on it. The height of this ramp, let's make it 2 meters. Now previously, what we have to do is recognize, and let's make this box 5 kilograms, is last time we'd have to realize that we need to know this angle here, theta, and there's a force going down, the mg, and what ends up happening is we need to break this up into components. We get mg sine of theta, and we get mg cosine of theta, but we also have a normal force. The normal force will also be the same as this component. So these cancel out. And so our net force is simply equal to mg sine of theta. And we either need to know the distance traveled and use our kinematic equations. And we saw this is quite complicated. However, conservation of energy allows us to solve this quite easily. We need to look at the before and after. So this is the before. If we look at the after, what happens after? Well, the box is going to slide down. and is going to be moving at some velocity at the bottom. So beforehand, we can calculate the total energy. The total energy is potential energy due to gravity plus the kinetic energy. Since we assume that it's at rest at the top of the slope, it's not moving and thus has no energy due to motion. So all the energy is in gravitational potential energy, which is equal to mgh. Its mass is 5 kilograms, 9.8 meters per second squared, and a height of 2 meters. And so that's equal to 98 joules. But we know that energy is conserved. Energy does not change at any point. It can only transform from one form to another. What happens is all the energy, potential energy, is being converted into kinetic energy. So we can do the same thing. Gravitational potential energy plus kinetic energy. Since we're letting the ground be 0 meters, mgh is 0, so that cancels out. All the energy is now in the form of kinetic energy. So the kinetic energy is 1/2 mass times velocity squared. So 1/2 times 5 kilograms times velocity squared, which is equal to 2.5 kilograms times velocity squared. And now we can solve for velocity. Divide by 2.5 kilograms on both sides. So 2.5 kilograms and 2.5 kilograms. That cancels it out on this side. And that gives us 39.2 meters squared per second squared. For the joule, 1 joule is equal to a kilogram meters squared per second squared, and we're dividing by a kilogram. That's equal to velocity squared. We then take the square root. The velocity is equal to plus or minus the square root of 39.2 meters per squared, or meters squared per second squared. For most of these problems, we don't concern ourselves with direction, so we can ignore direction. Why we get plus or minus is if we flip this around symmetrically, if we instead had the same slope, like this, and we put the box at the exact same height, it would fall down and be moving in the opposite direction. So symmetrically, as long as it starts at the same height, it's going to reach the same speed, but we have two scenarios. You can either go from here to here, or from here to here. And since I didn't indicate a direction, we're not really concerned with positive or minus. And this is equal to 6.261 meters per second. Alright, let's look at a pinball machine. Suppose we had a spring it's compressed. Let's say that the compression from where it originally was So it was originally here, and we compressed it back here. Let's make that 0.2 meters. And let's say that spring has a spring constant of 1, no, let's make it 10,000. 10,000 newtons per meter. How fast will the ball move? And let's make this a 5-kilogram ball. After the spring is released. So this is our before configuration. And let's look at after. After we let go, the spring will unravel some, and the ball is going to start moving at some velocity. So, the total mechanical energy, I'll call everything on the left side 1s, the mechanical energy on the left side will be equal to the mechanical energy on the right side. So that means the potential energy 1 plus kinetic energy 1 is equal to potential energy 2 plus kinetic energy 2. So we get, this is for a spring, so we get 1/2 times k times x1 squared plus 1/2 times mass times initial velocity squared. Now equal 1/2 k x2 squared plus 1/2 m v2 squared. So on the before, the initial x compression, I should do 1, is equal to 0.2 meters. The initial velocity v1 is equal to 0 meters per second. On the right side, our spring is no longer being compressed, so x2 is equal to 0 meters, and its velocity 2 is equal to v, or final velocity. So we can, since v1 is 0, this term gets removed. Since x2 is 0, this term gets removed. And so we end up with a simplified equation. 1/2 k x1 squared equal to 1/2 mv2 squared. Whenever I see equations like this, I look to see if there's any common variable or term on both sides, and there's a half. So I can multiply this whole equation by 2. This 2 will then thus cancel out the 1/2, and I get k x1 squared equal to mass v2 squared. Solving for v2, I would divide by mass on both sides. Masses cancel out. Giving me, and I'm going to rearrange a little bit, v2 squared is equal to k x1 squared over m. Again, direction doesn't really matter. Yeah, or at least whenever you look at the direction, it's moving to the right, and I'm letting right be positive, so I can select, whenever I think the square root, I can select just the positive term. So v2 is equal to k x1 squared over mass, and the square root of all of it, whenever you take the square root of both sides. So velocity is equal to the square root of 10,000 per k. Our x was 0.2, and we're squaring it, divided by our mass, 5. and we get a value 8.944272 meters per second. Alright, let's do a slightly more difficult equation. So suppose we have a roller coaster. Let's suppose that at the start we have a 50 kilogram box moving at 5 meters per second. And let's let our reference point be here. And this is supposed to be on the reference point. So there are 0 meters. Let's let this height be 10 meters. And let's let this height be 4 meters. And the question is, how fast is the box moving when it reaches the top of the loop? So we need to look at our initial conditions. So we need to compare between this point, I'll label 1, and this point here, I'll label 2. So we need to look at the total energy at 1 and the total energy at 2. We know that the total energy doesn't change throughout this. Mass stays constant. So I'm going to label this H1. This will be H2. This will be the velocity 1. And this box is going to be moving. It's going to be moving at some speed. Its speed is going to be d2. Again, for these types of problems, we're not really concerned with direction. So we're going to ignore direction for now. You should just know the direction based off what your intuition tells you about the motion. So the mechanical energy at the beginning would be the gravitational potential energy plus the kinetic energy. And that's going to be equal to the same thing on the right, just at position 2. So we get mg h1 plus 1/2 mv1 squared. Here we're going to get mg h2 plus 1/2 mv2 squared. Note, the mass stays constant, so I don't have to put numbers on it. But look at what's in every single term. It's the same variable. The mass did not change. That means we can divide the entire equation by m. M divided by m cancels it out here. And we can simplify this down to gh1 plus 1/2 v1 squared, gh2 plus 1/2 v2 squared. So the final speed actually doesn't depend on mass. That's because if you drop the heavy boulder versus a feather, if you ignore friction, they're going to accelerate down at the same rate. And because everything accelerates down at the same rate, things are falling, even on a slope, it doesn't really depend on mass. Note, in the real world, we have friction, and friction is going to be equal to some constant. So frictional force equal to some constant, the Greek letter mu, times the normal force. And the normal of the force depends on gravity. And so here is equal to the gravitational force. Going back to the sliding box example, is mg cosine theta. And that's the reason why in real life it does depend on mass, but if we ignore friction, it doesn't. So we're trying to solve for the final velocity. So move this to this side. So gh1 minus gh1 plus 1/2 v1 squared plus, is equal to 1/2 v2 squared. Multiply both sides by 2. One thing I note, both of these terms have a g in it, and this is supposed to be 2. So I'm moving this to this left side, so it becomes a minus. So I'm going to just factor this. That's g h1 minus h2. Note, you don't have to do this. So I'm going to multiply both sides by 2. So I get 2 over here. The 2 will cancel out with this, give me v1 squared here. And I'm left with this. So the final equation is equal to 2g, the change in height, plus v1 squared, square root, and plus or minus in front. We're going to just ignore and just look at the speed, so we'll get absolute value. So plus or minus the square root of 2 times 9.8 times 10 minus 4 plus the initial speed was 5 squared. And at the top of the loop, we get a final speed of 11.9 for 15 meters per second. Note, it wouldn't have mattered if there was several loop-de-loops throughout here. It didn't matter if this went up, down. The final speed here only concerns itself with the final height, and it does not depend on how the journey was made. Again, in the real life, if you were to add lots of loops, you're adding a lot more surface. If you had friction, that means you're losing a lot of your energy due to friction, and thus it wouldn't matter on the journey. But since we're ignoring friction, the final only depends on the height, which means I come over here and then did this, a really sharp hill. The height at the velocity right here, since it's 4 meters up, would also be 11.9415 meters per second. We could also calculate the final speed at the bottom right here, doing the exact same thing. Now our final height is 0, so we already solved this. Our final height is 0, so we can plug in 9.8. Our initial height was 10 minus 0 plus our initial speed was 5 squared. And doing this, we can see that our final speed is 14.8661 meters per second at the very end. I believe that's enough information to solve all the homework, which I'll release on Google Classroom.